This video is to review the idea of U substitution, which is the last topic in chapter 5 of the calculus book. So it's, for many people, it's the last topic that you covered in calculus 1 before coming to calculus 2. To understand U substitution, we're going to start with making sure everybody understands the basic antiderivative rules, and these will be different depending on what kind of calculus course you came in with. If your calculus course didn't have much focus on trig, then this middle section will be a little mysterious. Many people don't get to the inverse trig functions that you see at the bottom, but this is a complete list of everything that people have in different calculus 1 courses. So these are the antiderivative rules that we'll start off using, but you may want to take a list like this and just put it in your notebook someplace where you can reference it easily at the beginning of the semester, and then over the course of the semester you'll have get the hang of all of these. The idea of substitution, if you recall, is that we would like to change the variable in the integration problem so that the entire integrand is simpler, and simpler with respect to our antiderivative rules. This is a place where a lot of people have issues, and a lot of times the issue is stemming from the fact that the dx in the integral notation doesn't really seem to have much meaning to people. If you review the video on integration concepts, you'll see where the dx comes from, and it is an essential part of the theory. But more than that, it specifically can cause problems if you ignore it, because you won't be able to do U substitution. So here's the idea. We'd like to replace a compound expression like 5x plus 2 with a simple expression like u. Want to be able to do that. And so in this case, oops, need the right color. This would just be 5 times e to the u dx. If you were one of the people that drops the dx or du or whatever off of your integrals, then you would never notice at this point that this integral has a mixture of variables. It has u's and x's mentioned in it. And whenever that happens in a calculus, single variable calculus course, we really can't continue the problem until we've resolved what all of those things are. Only one thing can be the variable in the integration. So it can't be both u and x at the same time. So what we need to do is figure out the relationship between the dx that's in the original integral and a du that would be in an integral in terms of u. So to get that relationship, it always comes from just taking the derivative of the u and x relationship. So in this case, du dx equals 5. But we always want to write this as a relationship between differentials. The differential is what this guy is called. This little du and dx things individually are called differentials. And so the fact that du over dx is 5 means that the differential du is 5 times the differential dx. Now this does have a meaning in terms of the way the derivative works. You're basically saying that for every 1 unit change in x, the change in u is 5 times that. And if you think about what slope means, that's exactly what how you would interpret slope. So it's not a crazy interpretation, but it feels a little weird to treat this thing like a fraction formally. But we're not going to do it in all kinds of weird ways. We're just going to always do it this way. Take our derivative statement and turn it into a relationship between the differentials. And so what I'm going to suggest, and I hope if you have trouble with these that you'll follow my advice, is that we write all of the information that we intend to use for our substitution in a box, and we put it up at the right-hand side of our of the problem so that we have it for easy reference. Because our goal in doing substitution is really simply to change equal things to equal things based on what the box says are equal. So in this problem, for example, I could rewrite the integral here. Instead of 5 times e to the u times dx, I could write it as e to the u times 5 times dx. That's the same thing, just in a different order. The advantage of writing it that second way is that I can now see that I have 5 dx here, and I have 5 dx here, and so those match. Similarly, the 5x plus 2 here and the u are equal because of this equation. So what that means is, in my integral, the 5 dx, the thing in the box, is really just equal to du. I guess I should have waited to circle it. Hang on. So the 5 dx part is equal to du, according to this guy. And the 5x plus 2 part is equal to u, according to this guy. And so what I've done is I have gotten everything in this integral, the original integral that had x's in it, is now completely in terms of u. And so now I can just use the antiderivative rule for the exponential function. The antiderivative of e to the u is just e to the u. I can check this. I guess I should, if our original question was written in terms of x, then it's only polite to give our answer in terms of x. So instead of the answer being e to the u, I should say the answer is e to the 5x plus 2 plus a constant, so that the variables in the answer match the variables in the problem. So to check, we can take the derivative of the answer we got, and we know from the chain rule, say chain rule here, that the derivative rule for e to a power is just e to that exact same power times the derivative of that power. And the derivative of 5x plus 2 is just 5. So this will be e to the 5x plus 2 times 5, and that does match our original integram. Notice that when I check this, I had to use the chain rule, that it's not a coincidence. The U substitution method for integration is exactly the same thing as just doing the chain rule backwards. So not only should you, when you check, should you be using the chain rule, but the inside function, the thing we call the inside function, when you do the chain rule, is going to match the U in your substitution, for sure. So So I do recommend you check these, because you also will get to practice using the chain rule by doing that. All right, here's one that looks more complicated. Again, we're being told what the substitution should be. And so I'm going to follow the same method I did before, where I get a relationship between the differentials du and dx. I do that by finding the derivative of the substitution, so 3x squared plus 2, and then write that as a relationship between the differentials. So moving this dx over to the other side, I'll have that. So let me make it a box. So in the box, I have my relationship between x's and u's and dx's and du's. And so now my goal is to write this integral in terms of only u's and du's. So let me first, well, actually, let me just rearrange it. That makes sense to do first. What I notice here is that this 3x squared plus 2 and dx together, 3x squared plus 2 dx, 3x squared plus 2 dx, is exactly what's over on this side. So the very first thing I should do is just write this in a different order, so that the stuff that I can see in my box going together look like they go together, and that'll make me feel like I'm sure I've accounted for everything. So so here we go. This relationship tells me that this thing can be turned into a du. And this relationship tells me that any place I see x cubed plus 2x plus 1 can be changed into just u. So that's here. So there's x cubed plus 2x plus 1 changes into u. So so as before, all that I'm doing is in the integrand, I'm changing things equal for equal, and the things that are equal are the things that are up in my box on the right. And now I have everything in this integral is in terms of u. So u to the 7th du is 1/8 u to the 8th, and that's 1/8 times this long thing to the 8th. I would recommend that you check. You'll find the chain rule gets used. I won't do it here, just in the interest of time. But if you check by taking the derivative of the answer you got and seeing if it's equal to the integrand, it should work out perfectly, and you should feel yourself using the chain rule the same way we did on the previous slide. Now, if there are numbers involved, if it's a definite integral, there's one more layer that we have to work with, and that is that even though it's not written explicitly, the limits of integration are actually values of x. If you think about the interpretation of the integral as the area between the curve and the x-axis over the interval, if you draw a picture of that, then the 2 and the 6 in this problem are x-coordinates. They're values along the x-axis. And so that's another place where you have a reference to the variable x in the problem, even though it doesn't explicitly say that. So we have to look out for that. All right, so I'm going to use the substitution u equals 3x minus 2. And as before, I'm going to take the derivative of that written in this du dx notation. The du dx will be equal to 3. And then that means when I write this as a relationship between the differentials, moving this dx over to the right makes that du equals 3 dx. And again, I'm going to put that in a box at the top, so I can refer back to it. So there it is. So now in my integral, I can do the transformation because again, well, first I'm going to rewrite the fraction. You can see how I've taken this integrand and rewritten it so that it's 1 over the denominator times 3 dx. And again, the reason for doing that, like before, is that 3 dx is sitting right there. And so I can see that in terms of matching things up, that's what I'm going to want to do. So that first step is not really doing anything other than rewriting it so that I can see visually where all the pieces are going to come from when I substitute equals for equals. So this relationship, du equals 3 dx, there's the 3 dx, and it's going to turn into a du. This relationship, u equals 3x minus 2, there's the 3x minus 2, it's going to turn into u. So if we didn't label the 2 and the 6 on the definite integral, we might believe at this point that everything is done, that everything is in terms of u, but it really isn't because of these guys really referring to x-coordinates. So, so the way we can deal with that is by changing them from references in terms of x into references in terms of u. And that's a very easy thing to do because we know exactly how u and x are related. In other words, if you tell me a number value for x, I can use the box thing that has a star next to it to find the corresponding number for u, and vice versa for that matter. But it's easy to translate the x equals 2 and x equals 6 into u values as well. Oh, sorry, that actually just says what I just said. What I'm going to do is take that as translations of x equals 2 and x equals 6 to be in terms of u. I'm going to add those to my box as well. I want to put everything at the top in a box that relates, that shows how my x's and u's relate to each other. So here it is. Because u equals 3x minus 2, that means when x equals 2, I can put 2 here for x. 3 times 2 minus 2 is 4. So when when you put a 2 there for x, this will say u equals 4. When you put 6 here for x, this will say u equals 16. So that's what I'm doing. That's what I'm doing here. So if I can just one more time do the mapping, the 3x minus 2 becomes the u because of this. The 3 dx becomes du because of this. And the x going from 2 to 6 becomes u going from 1 to 4 because of these. So now I am done. The antiderivative of 1 over u is the log of u. And so evaluating the log of u from 4 to 16 gives me log of 16 minus log of 4. What we would categorize as intermediate techniques would be things where it doesn't just work out that the exact thing you need to have match your d between du and dx is exactly what's in the problem. Those previous problems were engineered to work out as nicely as possible, but let's see what happens if things aren't as quite as neat as that. So if I make the substitution u equals x squared plus 1, then the integrand, if I just do that, then I'll have something like this. So the x squared plus 1 became the u because of that equation. Now we already have learned that we also need to account for how the differentials change. We need to look at the relationship between dx and du, and we do that by taking the derivative of the substitution instance and then manipulating it. So if I wrote that as a paragraph, it would look something like this, but that's hard to follow and hard to process, and so that's why I tend to write this as a top. If u is x squared plus 1, then du is 2x dx, and that means I can rewrite that as 1/2 du equals x dx. This step, by the way, what I'm doing here is I'm taking this as an equation and I'm multiplying both sides by 1/2. If you multiply both sides by 1/2, it turns into this. It's one point of emphasis here is that these really are equations, and so you can do whatever you want to them as long as you do it to both sides and as long as it's useful to the problem. So for example here, if you want to just subtract 1 from both sides, if that would be helpful, you can do that. If you want to multiply both sides of this by 3, if that's helpful, you can do it. Same thing here. You can multiply both sides by a number, and it doesn't change the equation. So you can manipulate these equations in the box, and you should just only do it if it's useful to do it. The reason that this is useful is because when I look at my original integrand, I can see an x dx just sitting there. Right? It's already written, they're already together. There's x dx right there. So this substitution will allow me to replace that x dx with 1/2 du. So I can see that that's going to be a useful way of thinking of that relationship. So here it is where I'm doing all the steps. So again, this is my relationship between du and dx. So here's the x dx from the original integrand, turns into 1/2 du because of that. Here I have the relationship between u and x. So here's x squared plus 1. That turns into a u. So after I've done both of those things, I now have an integral that's only in terms of u, and it's just a power of u, so that's the easy power. And I end up with 1/12 u to the 6 plus constant, and substituting back in for u, that means I have 1/12 times x squared plus 1 to the 6 plus constant. Don't forget you should check. If you do check, I'll just put it, I have it already typed here, so I'll put it on the screen. What we expect to see is the chain rule being used. So here it is. When I take the derivative of this guy, the 1/12 gets ignored. It just sits out in front. I'll always say we're ignoring these constant multipliers. That doesn't mean we're deleting them. Deleting them is not ignoring them. That's more aggressive. Ignoring them means leaving them there. So if I ignore the 1/12, I leave it alone. This 6 comes out in front. It's right there. The power goes down by 1, and then we multiply by the derivative of what's inside because of the chain rule. So the derivative of the x squared plus 1 is 2x. The 2 times the 6 times the 1/12 all go away, and we end up with exactly the integrand we started with, as we wished. Here is another intermediate problem to practice. This works exactly the same as the one before. Feel free to pause here and write this down and give it a try. I'll show you the answer at the end, but I'm not going to take the time of the video to go through it. This is a more advanced example. And what I mean by that is in this one, you actually do need to manipulate everything, but you really shouldn't manipulate things until you have thought about why you're doing it. In other words, you want to try to make as much substitution as you can and then see what else you need to do. And once you know what else you need to do, then go back to your original substitution instances and see if you can figure out how to do it. So for example, in this problem, just like the other one, we're going to have, if u is x squared plus 1, then du will be 2x dx. That's exactly what happened in the other one. And so I learned in the other one that once I have that, I'm allowed to manipulate this if it's helpful. So that would be an okay thing to do if it's helpful to do so. I don't know for sure in this case if it is, but that would be okay. And I mentioned at the time that it would be okay to manipulate this one as well. There was no reason to do that in the other one, but in this one, and in any one that someone would consider to be an advanced substitution problem, the reason they end up being advanced is probably because there's something to do here. So that's your hint. Like I said, I'll let the video sit for 5 seconds or so on each of the solutions to these last two problems, but I'd recommend you give them a try first and then check your answers.